Hello friends, welcome to Engineers Digital Studio. This studio has been developed for those students who are not able to afford very high fee of the coaching institution, are located at remote places in India, but have access to the internet facilities. Today we are going to learn a very small topic of circuit analysis that is called transient response. This topic is very important for almost all the competitive exams. You will have at least 1 to 2 questions from this topic in every exam. You talk about GATE, you talk about engineering services, talk about civil services, talk about ISRO and so on. I will give you very few tips, very few shortcuts to solve the questions on transient response. I will take only two types of circuits for transient response today, that is RL circuits and RC circuits, and those are basically the first order circuits. The natural response of any first order circuit can be given by xt equal to x infinity minus x infinity minus x0 plus into e raised to power minus t by tau. This is the general response of any first order circuit. Now let us see what is x infinity, x0 plus and tau. X infinity is basically the response of the circuit at t equal to infinity. That is normally a steady state in the circuit. So x is the response of the circuit at t is equal to infinity. Then x0 plus. X0 plus is basically response of the circuit at t equal to 0 plus. This 0 plus means the instant just after the switching, when either you open the switch or close the switch, that is t equal to 0 plus, just after the switching instant. And tau is called time constant of the circuit. So whatever is the type of circuit, there are certain points to be remembered for solving such type of questions. When you talk about first order RL circuit, the circuit should consist of a DC source, a switch, an inductor and a number of resistors, maybe one resistor or maybe number of resistors. Inductor should be single, or if you have multiple inductors in the circuit, you should be able to replace those inductors by their equivalent single inductor. So I will start with the very first circuit, that is first order RL circuit. So the response of first order RL circuits. So when you talk about the first order circuit, first order RL circuit, the response can be a voltage, it can be a current, but general expression of first order RL circuit is given for current response, and from the current we can find voltage across any element or current through any element of the circuit. So the current through inductor in a first order RL circuit is given by ILT, that is current as a function of time, is equal to IL infinity, that is current through the inductor at t is equal to infinity, minus IL infinity, again that is current through the inductor at t is equal to infinity, minus IL0 plus, that is current through the inductor at t equal to 0 plus, into e raised to power minus t by tau. So instead of repeating it again, I am just explaining. IL infinity is current through the inductor at t equal to infinity. IL 0 plus is current through the inductor at t equal to 0 plus, and tau is time constant of the circuit. The time constant of the circuit tau for first order RL circuit is defined by, that is L by R equivalent, where L is of course inductance, R equivalent is nothing but, this is the Thevenin equivalent. R equivalent is Thevenin's equivalent seen across, that is Thevenin equivalent resistance seen across the terminals of the inductor. Remember this. What we do, we will see the resistance seen across terminals of the inductor, and that is Thevenin's equivalent. We will see the procedure how to find the Thevenin's equivalent resistance, but for the time being just remember tau is the time constant, that is L by R equivalent. L equivalent is Thevenin's equivalent resistance seen across the inductor terminals. Now directly I will go to the circuit. Let us see how to find this. So for finding out the response of any first order RL circuit, I have to find this IL infinity, that is current through the inductor at t equal to infinity. Then I have to find this second component, that is IL 0 plus, that is current through the inductor at t equal to 0 plus. Then I have to find tau. Tau, of course, you know what is inductance. So R equivalent you can calculate by applying the Thevenin's concept, Thevenin's theorem, to find out the resistance. So let us see the circuits. I'll take few examples. Of course, these examples are important for exams, different exams, especially GATE and engineering services. Take one simple circuit. Suppose I have a voltage source, this. There is a resistance connected in series with this voltage source. Now there is a bipolar switch. Initially this switch is connected across this point, that is, they say terminal 1, this is terminal 2. Now at this terminal, at terminal 2, we have another source connected in series with a resistance like this. Say this is 1 ohm, this is 2 ohm, this is 10 volt, this is 20 volt. Then there is one more resistance connected in series. Then there is another resistance and an inductor connected across the resistance. Now say this resistance is 1 ohm, this is 2 ohm, this is the circuit you have. Suppose you have to find out current through the inductor, that is IL, for t greater than 0. Now let us understand the switching operation. Suppose initially switch is connected at point 1 and you shift at point 2, terminal 2 at t equal to 0. This is the circuit you are given. You have to find out current through the inductor for t greater than 0. Now just recall that general expression of current through the inductor, that is IL as a function of time is equal to IL infinity minus IL 0 plus, IL infinity bracket close minus IL 0 plus into e raised to power minus t by tau. So this is the general expression we had. Now I will try to calculate IL 0 plus. Remember, current through an inductor cannot change instantaneously. So if I find the current through the inductor for t equal to 0 plus or 0 minus, that current at t equal to 0 minus will be same as the current at t equal to 0 plus. Why? Because the current through the inductor at t equal to 0 minus will be same as the current at t equal to 0 plus, because current through the inductor cannot change instantaneously. So, to find this current at t equal to 0 plus, if I find the current at t equal to 0 minus, that will serve my purpose. So, how to find current at t equal to 0 minus? Let us see the procedure. I will try to draw the equivalent circuit at t equal to 0 minus. At t equal to 0 minus, remember, the circuit is always at steady state operation at t equal to 0 minus, that is just before the switching element instant. Second, at t equal to infinity, that is after long time of switching operation. Now, there are certain points to be remembered here. When circuit is under steady state operation, the inductor behaves like a short circuit. So, there are two instants when circuit is under steady state operation, at t equal to 0 minus and at t equal to infinity. So, at these two instants, this inductor will behave like a short circuit. So, when you draw the equivalent circuit for t equal to 0 minus, you can see the switch is at terminal 1. So, I will draw the equivalent circuit like this. We have 2 ohm resistance, then terminal 1, a switch, then a resistance of 1 ohm, then resistance of 2 ohm here, and inductor. And I told the inductor behaves like a short circuit at t equal to 0 minus. Now, a voltage source of 10 volt here. So, the equivalent circuit for t equal to 0 minus will be like this. Now, the current through the inductor, of course, this is inductor, but behaving like a short circuit. The current through the inductor at t equal to 0 minus will be IL 0 minus. Now, you have to find this current. Please see this. This resistance of 2 ohm is bypassed by the short circuit. So, this whole current coming from the 10 volt source will be flowing through this path. There will not be any current through the 2 ohm, this 2 ohm resistance. So, IL infinity can be calculated direct, IL 0 minus can be calculated directly, that is IL 0 minus is equal to 10 by this resistance, that is 2 plus 1. So, this is 10 by 3 ampere. So, current through the inductor at t equal to 0 minus is 10 by 3 ampere. But I told current through the inductor cannot change instantaneously. Therefore, I will simply say IL 0 plus is equal to IL 0 minus, and that is 10 by 3 ampere. So, out of these 3 parameters, I have calculated this parameter. I am repeating the procedure. Draw the equivalent circuit for t equal to 0 minus, replace inductor by the short circuit, and calculate IL 0 minus, and of course then IL 0 plus is same as IL 0 minus, because current through the inductor cannot change instantaneously. Now, I have to calculate IL infinity. For calculating IL infinity, the switch is at position 2. When switch is at position 2 at t equal to infinity, and I told the circuit, the inductor behaves like short circuit at steady state. At t equal to infinity, there is a steady state. So, this inductor will behave like a short circuit at t equal to infinity. So, the equivalent circuit for t equal to infinity will be like this. You have the switch at position 2, a resistance of 1 ohm, a voltage source of 20 volt, then a resistance of 1 ohm here, and again you can please see this resistance of 2 ohms is again bypassed by the inductor at t equal to infinity also. Now the current through the inductor is IL infinity. So from this circuit, of course, you can calculate the current at IL infinity equal to 20 by 2. And of course, that's very simple to calculate. That's 10 ampere. So out of these 3 parameters, I have calculated this and this. Now I have to calculate tau. So let us see how to calculate tau. I will rub this. So for calculating the time constant of the circuit, of course, first of all, I have to find out the equivalent resistance seen across the terminals of inductor. So remember, time constant is calculated for t greater than 0. That is after the switching instant. For t greater than 0, the position of the switch is at terminal 2. So for calculating Thevenin equivalent resistance seen across the inductor terminal, there is a procedure. Procedure is, I am just trying to recall. For calculating Thevenin equivalent resistance seen across the inductor terminals, short circuit the independent sources, voltage sources of the circuit. And of course, in this circuit we have only voltage source, so replace voltage source, independent voltage source, by the short circuit. And if there is a current source, replace that independent current source by the open circuit. So in this case we have just voltage source, I will replace this voltage source by the short circuit. Then open the terminals of the inductor and see the resistance across the terminals of the inductor. Let us see how to do it. So draw the equivalent circuit for, that is equivalent circuit for R equivalent, that is Thevenin equivalent resistance. So it will be like this. Switch is at position 2. So I will replace the voltage source by the short circuit. This is 1 ohm resistance. Again 1 ohm resistance. Here we have 2 ohm resistance in parallel to the inductor, and open the terminals of the inductor now and see the resistance seen across the terminals. So that is R equivalent. So it is very simple to calculate now. You have these resistances in series, equivalent resistance 2 ohms, and this 2 ohm is in parallel to the combination. So just to expand, I will write it R equivalent equal to 2 ohm in parallel with series combination of the 1 ohm resistances. So it will be like this. So this will be nothing but 1 ohm. R equivalent is 1 ohm. You have the inductance. So the time constant of the circuit, I will write now the time constant of the circuit, tau will be equal to L by R equivalent. So I have already calculated R equivalent here. So this will be 2 by 1. This is equal to 2 seconds. So my work is done. I have calculated nothing but all the 3 parameters of the current through the inductor for t greater than 0. Therefore, I will write current through the inductor for t greater than 0, ILT is equal to, that is IL infinity. What was that? That is 10 ampere minus 10 ampere minus 10 by 3 into e raised to power minus t by tau. You will have the tau, that is 2. So you can further simplify this. ILT is equal to 10 minus, how much is this? That is 30 minus 20, that is 20 by 10, 20 by 3. 30 minus 10 by 3, that is 20 by 3 e raised to power minus t by 2. This is nothing but current through the inductor for t greater than 0. So this is how you can calculate current through the inductor for t greater than 0 in any first order RL circuit. Now we will see how to find voltage across the inductor for t greater than 0. So voltage across the inductor for t greater than 0 is determined by one simple relationship, that is nothing but VLT. You know that is voltage across inductor is nothing but DILT by dt. And you know the expression of ILT, that is L d by dt, and you know what is that? IL infinity minus IL infinity minus IL 0 plus e raised to power minus t by tau bracket close. So now please see this, when you differentiate it you will get L by tau IL infinity minus IL 0 plus into e raised to power minus t by tau. I hope you understand this. This will be 0, differentiate this, you will get minus minus plus sign L by tau. And you know what is tau? That is nothing but L by R equivalent. So voltage across the inductor for t greater than 0 will be simply R equivalent, and you know what is R equivalent? That is Thevenin's equivalent resistance seen across the terminals of inductor. So R equivalent into IL infinity minus IL 0 plus e raised to power minus t by tau. So you can find out the voltage across inductor by simply using this formula. Again, for calculating VLT in any circuit, I have to find out IL 0 plus. The procedure we have already seen in the previous example. IL infinity, the procedure we have already seen. The tau, R equivalent. R equivalent is of course calculated for calculation of tau itself. So again, by calculating the three parameters R equivalent, IL infinity, IL 0 plus, I can find the voltage across the inductor as well. Now we will see how to find the current through any of the resistance in first order RL circuit. So let us see the procedure. Remember again, the procedure is same just like inductor. Suppose I have to find the voltage, the current through a resistance, any resistance of first order RL circuit, and that is given by IL, that is IR, current through any resistance, as a function of time is equal to, remember this is IR infinity minus IR infinity minus IR 0 plus bracket close e raised to power minus t by tau. Formula is same. Now instead of inductor I have replaced it by resistance. So for finding out the current through any resistance in first order RL circuit, remember this, in first order RL circuit I have to find IR 0 plus, I have to find IR infinity and tau. Remember again the certain points. Tau is nothing but L by, that is time constant of the circuit, L by R equivalent. Remember the expression of time constant is same whatever we calculated in the previous expression of current through the inductor. R equivalent is resistance seen across the inductor terminals only. You have to remember this point. For calculation of time current through any resistance in first order RL circuit, I have to calculate time constant exactly in the same manner that I did in case of current through the inductor. Tau here is time constant, which is nothing but L by R equivalent, and this R equivalent is the Thevenin's equivalent resistance seen across the inductor terminals only. So R equivalent will be same as in the previous case. It means the time constant of the circuit will remain same whatever you did in case of current through the inductor. Time constant will not change whether you are calculating current through the inductor, voltage across the inductor, or current through any of the resistance of the circuit. The expression of time constant is same. Now we will see the example again. So for calculating current through the resistance, any resistance of the circuit, I have to find this IR 0 plus, I have to find IR infinity, I have to find time constant of the circuit. So I will explain the procedure how to find this IR infinite, IR 0 plus in example itself, so that you understand how to find these different parameters. So of course we have already seen. Now let us take one example. Suppose I have one circuit. There is a voltage source of say 10 volt. There is a resistance. There is a switch and another source, say there is 20 volt. Just like previous case, I have removed resistance from here, then I have a resistance, then again a resistance, an inductor, say this is 10 ohm, this is 10 ohm, this is 20 ohm, and this is say 5 Henry. And I have to find number 1, current through the resistance for t greater than 0, and number 2, I have to find voltage across the inductor for t greater than 0. Just to explain how to find both the parameters simultaneously. Now the procedure, for calculating VLT, you know the expression. For calculating IRT, you know the expression. So now let us see voltage across the inductor. Voltage across the inductor is equal to R equivalent, then IL infinity minus IL 0 plus e raised to power minus t by tau, and current through a resistance IRT is equal to, you know the expression, that is IR infinity minus IR infinity minus IR 0 plus e raised to power minus t by tau. Tau is same. So for calculating these two parameters, I have to find IL 0 plus, I have to find IL infinity, I have to find out IR 0 plus, then IR infinity. Procedure, I repeat it again. Current through the inductor cannot change instantaneously. That was the very first step I talked in the previous example. Current through the inductor cannot change instantaneously. Therefore, for calculating the current through the inductor for t equal to 0 plus, or current through the resistance for t equal to 0 plus, I have to find current through the inductor for t equal to 0 minus. So let us draw the equivalent circuit for t equal to 0 minus. Remember, I told you previously also in previous example, the circuit is always under steady state operation at 2 instants. One, before switching operation, that is t equal to 0 minus, and at t equal to infinity. At t equal to 0 minus, I have to draw the equivalent circuit to calculate the current through the inductor at t equal to 0 minus. Now let us see the equivalent circuit for t equal to 0 minus. Suppose switch is here, I am just drawing it again. Suppose switch is at position 1 and it is shifted at position 2 at t equal to 0. Now at t equal to 0 minus, switch is at position 1, the equivalent circuit is like this. We have the switch at position 1, voltage source 10 volt, then 10 ohm, then resistance of 10 ohm, then resistance of 20 ohm, then inductor, and of course at t equal to 0 minus, I told inductor behaves like a short circuit because at t equal to 0 minus there is a steady state in the circuit. So current through the inductor at t equal to 0 minus is IL 0 minus, and it is very clear from this circuit. I can find IL 0 minus is equal to 10 volt by series combination of these two. Why? Because this resistance is bypassed. So 10 plus 10, so that is 1 by 2 ampere. Now we have already discussed current through the inductor cannot change instantaneously, therefore IL0 plus is equal to IL0 minus, and that is 1 by 2 ampere. So out of these parameters I have calculated IL0 plus, but remember this is the circuit for t equal to 0 minus. This is current through the resistance at t equal to 0 minus. Remember, I cannot take current through the resistance same as IR0 minus and at t equal to 0 plus. Reason is, current through the resistance can change instantaneously at one instant of time. At t equal to 0 minus, current is IR0 minus, and current through this resistance at t equal to 0 minus can change. It will not remain same, but current through the inductor will remain same. So I am repeating, current through the inductor cannot change instantaneously. So current at t equal to 0 plus and current at t equal to 0 minus is same. But current through the resistance can change instantaneously. Therefore, current at t equal to 0 minus is not same as current at t equal to 0 plus. So remember this point. So in that case, how to calculate IR0 plus? I could find IL0 plus simply by drawing the circuit at t equal to 0 minus. I cannot obtain IR0 plus directly. So there is one more step in this case. I have to draw the equivalent circuit for t equal to 0 plus for obtaining the current through the resistance at t equal to 0 plus. So let us see how to draw the circuit for equivalent circuit for t equal to 0 plus. Remember, I told current through the inductor cannot change instantaneously. So I have seen IL0 plus is same as IL0 minus, and that is 1 by 2 ampere. So when you draw the circuit for t equal to 0 plus, inductor is replaced by a current source of value equal to IL0 plus, and that is just for t equal to 0 plus only. So for t equal to 0 plus, inductor behaves like a current source of value equal to IL0 minus or IL0 plus. So while drawing the equivalent circuit for t equal to 0 plus, I will replace it by a current source. But remember, at t equal to 0 minus, this switch was at position 1. Now at t equal to 0 plus, switch will be at position 2. Reason, t equal to 0 minus was before switching. That was, switch was at position 1, and t equal to 0 plus, switch is at position 2. So the equivalent circuit for t equal to 0 plus will be, switch will be at position 2, the voltage source of 20 volt or resistance, of course 10 ohm, you know from the circuit, then the resistance of 20 ohm, then inductor, and I told replace the inductor by the current source of value equal to IL 0 minus or 0 plus, that is same thing. So IL 0 plus, and that is, you know, that is 1 by 2 ampere. Now I have to find current through the resistance, and now current through this resistance will be IR0 plus, because this equivalent circuit is for t equal to, and see from this, if you have to calculate current to this, there is a simple procedure. Say this is a node A, so I will apply KCL at node A. When you apply KCL at node A, reason, please understand, whenever there are 3 branches, so it is better to apply KCL at the node to find the current through the resistance. So VA minus 20 by 10 plus VA by 20 plus, and of course this is outgoing current, this is outgoing current, this is outgoing current, and that is half ampere equal to 0. You just simplify this, you will have 3 VA then 40 plus 10 equal to 0. So VA will be equal to 10 volt. So now current IR 0 plus will be equal to VA by 20, and that is nothing but 10 by 20, and that is also half ampere, 1 by 2 ampere. Now we have obtained IR 0 plus, we have obtained IL 0 plus. Next step is to find IL infinity and IR infinity. So the procedure is again same. At t is equal to infinity, circuit is under steady state operation. Inductor behaves like a short circuit, and remember at t equal to infinity, switch is at this position. So I will draw the equivalent circuit for t equal to infinity here, and simply this circuit can behave like this. Just replace this current source by short circuit because this was the inductor. Now current through the inductor is IL infinity, that is a steady state operation. Now this resistance is bypassed by the inductor, so IL infinity will be simply 20 by 10, that is equal to 2 ampere. Now IR 0 plus, it is very much clear from this circuit, this is bypassed, so current through this resistance will be, this is IR infinity, so IR infinity is equal to 0. Now we have obtained IL infinity, IL 0 plus, IR 0 plus, IR infinity. The only part to be calculated is tau. So to find the Thevenin equivalent resistance across the inductor terminal, I told you the procedure. What is the procedure? Equivalent circuit for, I will draw here itself, equivalent circuit for T equal to, for R equivalent rather. So for R equivalent, open the terminals. You open the terminals, see the resistance here, that is R equivalent, and remember for calculating R equivalent, replace the voltage source, independent voltage source, by the short circuit. So the R equivalent here will be equal to, that is parallel combination of 20 ohm and 10 ohm. So I hope it is clear. So this will be 20 by 3 ohm. So time constant of the circuit will be what? Time constant of the circuit, tau, will be equal to L by R equivalent, and what is L? That is 5 Henry. So tau will be 5 by 20 by 3. So that is nothing but 3 by 4 seconds. So we have calculated tau. Now we have calculated all the parameters required for calculating VLT and IRT. I repeat, VLT is nothing but R equivalent, that is nothing but 20 by 3, into IL infinity is what? That is 2 ampere. We have seen that was 2 ampere, minus IL 0 plus. IL 0 plus, the value of IL 0 plus we have already seen, that was how much? LC from the expression IL 0 plus, into e raised to power minus t by tau. And what is tau? 3 by 4 s. So 3 will be in denominator, 4 will be there. Similarly, for calculating for obtaining IRT, this is equal to, so if you remember, this was 1 by 2 ampere, so I will replace it by 1 by 2 ampere. IRT is equal to IR infinity, that was 0, minus 0 minus IR 0 plus, that was 1 by 2 ampere into e raised to power minus 4 by 3 tau. So you have calculated both for the circuit. So for calculating these parameters, I repeat the procedure now. Find the equivalent circuit at t equal to 0 minus, find current through the inductor at t equal to 0 minus, then find current through the inductor at t equal to infinity. Remember, at t equal to infinity and t equal to 0 minus, circuit is under steady state operation, inductor behaves like a short circuit. Then open the terminals of inductor to find R equivalent, replace the voltage source by short circuit and current source, if there is, that is by open circuit. Additionally, if you have to find current through the resistance, I have to draw the equivalent circuit for t equal to 0 plus also. Reason? Because current through the resistance can change instantaneously. Therefore, for calculating current IR 0 plus, I need to draw the equivalent circuit for t equal to 0 plus. And at t equal to 0 plus, inductor behaves like a current source of value equal to IL 0 minus or IL 0 plus. So that is how you can solve these questions. So now you can try few questions from previous exams and try to find out the solution. Thank you very much.